All right, guys, so we are back. So as I was saying earlier, is that whichever line you can fold the image along such that it folds and fit perfectly, the left side folds and fit perfectly on the right side. That line through which you fold it is known as a line of symmetry, right? And the shape is reflection symmetric along that line. So this definition is saying a figure is reflection symmetric over a line L if and only if it coincides with its reflection image in the line L. The line is called a line of symmetry of the figure. So in this case, the line of symmetry of the figure would be the line AC, because you can fold the figure through that line, and B would map perfectly onto D. All right. Now, so we know that AC is the perpendicular bisector of the line BD. So remember, your line of symmetry would also be your mirror line, because it will cut the line BD into two equal parts, right? So it is a perpendicular bisector. So AC bisects the angle BAD and C and BCD. Now the triangle ABC and ADC are congruent. Anybody remember what the word congruent means? Anybody? Let's weigh some.
Yes, sir.
What's the word congruent mean here?
But they're doing the same thing, sir.
Not doing the same thing. It means that they are the same. They are the same in terms of their shape and size.
Okay, sir.
They are not focusing on the orientation now, but the same shape and the same size. The only difference here is that they have different orientation, but same shape and size mean congruent, sameness, right? So we are saying that the triangle, ABC, the triangle A, B, C, this triangle has the same shape as the triangle ADC. So if we now check out the triangle ADC, we're saying that it is the same, or if you want to say, so it's the same, they are congruent, they have the same shape and size. Now, one of the things I want to bring to your attention, guys, congruent is sometimes confused for similar. Now, similar triangle means that they have similar shape, but not necessarily the same size, right? So when it is congruent, it means you have the same shape and the same size. When they are similar, it can be congruent and similar, but it can also have different shape and similar, not different shape, different size, and also be similar at the same time. All right, so with that said, now the circle, the circle is reflection symmetric at any diameter. What does that mean? Anybody can tell me?
Sir, repeat that again for me, please.
The circle is reflection symmetric about any diameter? Anybody knows what that means? All right, let us think about a circle. So if we draw a circle here, now what is the diameter? What's the diameter?
Half of the circle, sir.
No,
Oh,
diameter is not half of a circle. The diameter is a straight line through the center of a circle. You get what I'm saying, Miss?
yes, sir.
Half of the circle is a semicircle, but the diameter is the line.
That is running straight through the center of the circle.
Right? So that's the diameter, that line.
Yes, sir.
So we say that the circle is a reflection symmetric about any diameter. So if it is reflection symmetric about any diameter, it means that you can fold it along any diameter and it will overlap and sit perfectly on the other side. You get what I'm saying?
Yes, sir.
All right. So if you draw your diameter here and you fold it, the top side will fold perfectly on the bottom side. If you instead draw the diameter at some other point, so if you draw it from here, and the diameter is going through the center of the circle, and if you draw it there, you fold it along that side, it will still be perfect. And so any diameter that you draw it, you will have a symmetric, a reflection symmetric about that diameter. All right, guys, everybody should be clear on that. All right, moving along. Now, congruence. Now, this suggests that a translation can be affected by two reflections. We say a translation, T, is composed of two reflections. All right, what that means. Now, looking at this, two figures, L and M, are congruent if and only if there is a composite of reflection mapping L onto M. All right, what that means. If you have these two mirror lines and you start off with your pre-image, so this would be your pre-image, the one without the dash would be a pre-image, and you reflect it through this mirror line, then it will become this one, right? And if you reflect it again, then it will become this. But what you would notice about this now would now have the same orientation as this last one here. Same orientation. Now, what this looks like to you, if you, instead of doing two reflections, you could just slide from the pre-image down to here, and you will get a translation. As a translation would be a slide. Do you see that, guys? Nobody see what I'm talking?
Yes, sir.
Miss Green? Miss Green, are you hearing me?
Yes, sir.
Okay. So what this is saying then is that two figures L and M are congruent if and only if there is a composite of reflection Now, if you remember when we were doing functions, I would talk about composite functions. Then what we do was to put one function in the other function, right? So what we are saying here, if you should put one reflection into another reflection, you could get a translation. Is that clear, guys? Guys?
Yes, sir.
Okay, sir. Yeah.
So if you do one reflection with this mirror line and you flip it and reflect it here, and you do another reflection with a mirror line L, then you will get this. So it would now turn out to be a translation. So here they tell you that we say a translation T is a composite of two reflections, and write T is equal to the mirror line M composite with the mirror line L. So T is the translation, and these are the composite of reflection. And so the translation is equal to the composite of two reflections. All right, guys? And so we'll get that. All right, here now we're going to be looking at rotation. Now, rotation, I would have mentioned before that you need some kind of axis on which to rotate. Now, if you have something like a string and you tie a stone to the end of it and you swing it around your head like an helicopter, then what would be the where would be the center of rotation? Guys?
Would be the center of what, sir?
Where would be the center of rotation?
At the point.
Imagine you have a string, you tie a stone on it and you're wheeling it around like an helicopter. Where would be the center of the rotation?
Sir, like
Where
where the zero or the point is.
We're not talking about the zero.
Where it first started, sir.
You must learn to listen to the question. I'm saying that if you have a string and you tie a stone on it and you're wheeling it around like a helicopter, where would be the center of rotation?
Sir, would it be where it first started?
The center would be where the person is standing, who is spinning the thing. Because the person would be in the middle while the thing is going around. So wherever the person is standing, that would be the center. Because that's, if you think of a wheel, where would be the center of rotation of the wheel? Right at the axle, right? You get what I'm saying?
Yes, sir.
So when you're rotating this triangle, you're spinning it around like a on a string now. So where whatever is in the middle at where the string is, at the origin. And I guess this is what Ms. Waysome was saying, where it starts. But I would rather to say at one end point. Well, if you want to call it the starting point, no problem, Ms. Waysome. But this would be where the center is while these are going around. All right, now this rotation is showing what we call a composite of two reflections, right, as it moves around. So this would give you your definition for your rotation. So a transformation, R is a rotation, if R is the composite of two reflections, ML and MM, where the line L and M are not parallel. Is that clear? So that's the definition. All right, so the angle is called the magnitude. So what they're looking at is these two, the angle of C, CO to C. So the angle of CO to C. Let me see if I can make that clear for you. So if you draw the line from C to O to its image, then that angle, this angle, would be also the same as the angle BOB. So if you're going from B, let me use a different color. So if you're going from B to O to B in this case, and if you're going from A to O to A, using also another color. So you're going from A to O to A double dash. All of them going to A double dash, right? What you would notice here is that all of these angles would be the same. So the angle from the first angle, C to C, that would be the same. Or if you call that A to A, use another color. And C to C would almost look the same. And B to B, we are saying that all of these angles would be the same size. So if this is theta, all of them would be equal to theta. All right, guys. And notice here, it is not the triangle A dash and B dash we are working with. We are working with the double dash one. And when you notice this one, the triangle has the same orientation throughout the rotation. All right, so moving on. Any question, guys? All right, so here we have finding the center of rotation. To find the center of rotation, find the perpendicular bisector of the line joining the pre-image and the image of 2 points on the rotation object, rotating object. So that's one. The center of rotation is at the point of intersection of 2 perpendicular bisector. All right, so I'll only have to show you this with an example. So here we have, what we know is that this line AB and the line AB, A dash, B dash, these are two, one would be the pre-image, which is AB, and A dash, AB, A dash, B dash will be the image, right? Now, in order to find the center of rotation, what they're saying, you should draw a line from A to A dash. Then you draw another line from B to B dash. right? Now you're going to draw a line which is perpendicular to AB, meaning the line that you're drawing here has to cut A and A dash. It has to cut this line A to A dash into two equal parts, and it has to be at right angles. So if you draw a line right angle right down the middle of this line, you draw a right angle to this down here. Now you do the same thing with this line, which is B to B dash. Draw another line here so that it is at right angle to B dash. Now, wherever these 2 points intersect, which you should clearly see, they would intersect right here at the middle here. So that would be the point of intersection for the two lines that are perpendicular. And at that point, where the two lines that are perpendicular to the line A to A dash and B to B dash, that point would be the center of rotation. Is that clear, guys? Guys?
Yes, sir. But sir, me not see we're no right angle formula, so.
All right, so the right angle that they're referring to would be the dotted line at right angle to the other lines. So this dotted line is at right angle to this line. You follow me, sir?
Yes, sir.
So that is right angle to this line, that is B to B dash. And this one is at right angle to this line. That is the line A to A dash. So
okay.
The line is at right angle to that. So you draw this line at right angle to A dash, and it cuts the A to A dash right in the middle. Same thing with this line, B to B dash, you cut it right in the middle. Now where these two dotted lines meet and wherever they cross, that's the center of rotation.
Okay, sir.
All right. All right, guys. All right, moving on. We talk about rotational symmetry. All right, so what it means to be rotational symmetric. All right, so a figure has rotational symmetry if it is coincided with its image by rotating about a point. Now, if you put a pencil right in the center where these diagonal line cross, and you spin the rectangle, rotate it. Let's say that this was a book and you put your finger here and try to spin it on that point of intersection. You could find that this A, if you rotate it all the way around one time, it could come back to the position of C. You follow? But this A, could this A get to the position of B by rotation?
Yes, sir.
Really? Oh.
I'm sorry, if I rotate, you can't catch a B.
No, it's not going to catch a B based on how it is. B, when you rotate B, B will go to B because they are diagonal to each other.
And I'll be past C for each of these, sir.
Yeah, but remember, the shape, the only way you will probably notice now, if you try an experiment, use a book.
Yeah. Okay.
Try to spin it around, label the sides, label the edges, A, B, and see which one of them would line up back with which point. You follow? And the point at which they come back to in line with, so that's what they call rotational symmetry. So a figure has rotational symmetry if it coincides with the image by rotating. So coincides really mean, if you move A around so that it come back where C is, that's a coincide line or coincide points, right? And so
Sir, would that be a full rotation or a half rotation?
it wouldn't be a full rotation, it would be a half rotation, but
Okay, sir, because that's why me say now A could have reached a B with one full rotation. Okay, sir.
it wouldn't reach B with a full rotation.
Right, sir. That's why I said the A where the A would meet the C would be a half rotation.
Right, it would be
Mm-hmm.
just a 180 degree. All right, so that's what it really means. So if the 2 points at the edges can become in line with one of the other points, then it is rotational symmetry. It has rotational symmetry. Now, the order of rotational symmetry of a figure is the number of ways in which rotational symmetry can be preserved. Now, the rectangle ABC have only 2 positions which are the same on the rotation in the plane. Therefore, the rectangle has 2 rotational symmetry. And as I was saying, one rotational symmetry would be when A come back to C. The other one is when B go to D. So it's only, and if you look at the right rectangle, it would have shown you how the rotation looks, right? Because remember, this was it before. So this is a pre-image. And this here now is the image after rotation. So when I rotate, the A now coincide back with the C. And the B now, the B would coincide back with the D. You notice? Guys? So if you flip this around, the C would come where the A is, and the D would go where the B is. That's all it is saying. So there's only 2 ways that these points will coincide. A with C and B with B. So it has order of 2 rotational symmetry. All right. Now, these are just properties that you need to know. I don't think you'll be asked these questions in the exam, but just in case, you should have knowledge of it. All right, our next transformation will be enlargement. All right, I'm just going to introduce enlargement, and then now I'll pick up back from enlargement when we meet next week, all right? So enlargement or reduction. Given a point O and a real number K, that should be then. So this is a typo. So this is supposed to be then A dash is the image of the point A under the transformation E, and E here would mean enlargement. If A dash lies on OA and OA and OA dash equal to K times OA. All right, that sounds like a lot of weird stuff. But all it is saying is that if you have an enlargement, so it's probably easier to show you a diagram than to explain what is being said. So if you have an let's say that an object now, what you could imagine is that this first triangle is a smaller triangle. But the bigger triangle would be an enlarged version of that smaller triangle. Now, what they're saying is that if the length from here, if here is O, and here is A dash. And here, so this smaller point would be A. So they're saying that AO is equal to K times OA, meaning that, let's say from here to here, let's say from here to here is, say, 2 centimeters, right? Now, K times AO, this is AO. AO is 2, or OA is 2 centimeters. Now, the length from O to A dash, you could imagine that this length would be another 2, right? So that means you would multiply this 2. So you could say it, to get to A dash, you would multiply 2 by 2. So 2 times 2 would give you 4. So the length of A dash, so if you replace A dash, or you replace K with a number, then A dash would be a scalar of A. I keep saying A dash. OA dash would be a multiple of OA. So let's say that the length of OA is, the length of OA dash would be 3 times the length of OA. That's all it is saying, right? So if you have 2 times 2 times 2, then this length of OA dash would be 4. So this length would be 2, but this length would be 2 times 2, which is 4. All right, so it might seem a little not so clear, but when we do some more questions, it will become clearer to you guys. So this is what it looks like on the enlargement. So what we are saying is that the length from here to here, which is the length from O to A, if that is, say, 3, and this length from here to A dash, O to A dash, and let's say that this is 9. So we are saying that you would have to multiply OA by 3. So 3 times OA is equal to OA dash, right? And we know that OA is 3. So we would have 3 times 3, which would be equal to 9. You're following what I'm saying, guys? So in other words, they're just saying how many times you can get OA out of OA dash. That's all it is saying. Because the more times you can, because remember now, if you're increasing the size of the thing, it means that you're magnifying it by multiplying. You're multiplying it by some number so that you're scaling it up. Guys, are you following? All right. It might not seem so obvious, but for enlargement, you're really multiplying by a number, and the number is known as a scale factor. All right. All right, so we'll stop here. And when we meet again next class, we will actually, I'll start back from this to give more clarification to it, guys. All right. Any question? All right, so I'm going to end class here.